Yes, you're welcome to my YouTube channel. Our topic for today is the contraction mapping principle. Another name for contraction mapping principle is the Banach contraction mapping. Now, what is the theorem? Banach in 1952 stated that when you have a complete metric space and you have a contraction such that the k ranging from 0 to 1, that whenever you have such combination, there must exist a unique fixed point such that f of x star will be equal to x star. That is the definition of fixed point. And number two, for any x naught in x, that the Picard iteration must converge to the fixed point. So these are the consequences of the Banach contraction mapping principle. Number one is that once there is a complete metric space, emphasis on the word complete, and there is a contraction, then the fixed point must exist and the Picard iteration must take us to that fixed point. Now, what is the definition of a contraction? A mapping T is called a contraction if there exists a K that is in between 0 and 1 such that the metric distance between Tx and Ty will be less than or equal to K, the metric distance between x and y. But for norm spaces, contraction mapping can be defined as the norm of Tx minus Ty being less than or equal to K, the norm of x minus y for all x and y that is in x. Remember that our x is non-empty. Now K becomes the contractive constant, or sometimes what you can call the Lipschitz constant. Now, consequences of our Banach contraction mapping. Suppose T is a contraction on a complete mapping metric space, then there must exist a fixed point. And secondly, the Picard iteration will easily converge to that fixed point. Now, the proofs have been written out for you in a very simple way. How do we go about this? Now, you choose an arbitrary x naught for a start when you want to run the Picard iteration. You choose your x naught for a start. That is your initial term. Then for you to get x1, you iterate with x naught. And for you to get x2, you iterate with x1. For you to get xn, just like that, you iterate with the value of the previous result. And when you do that, step by step, gradually, you're going to arrive at k raised to power n of the metric distance between x naught and tx naught. Now, continuation of the proof shows that xn is a Cauchy sequence. Now, since x is complete, we are saying that the sequence converges to a fixed point. The sequence generated by Picard converges to the fixed point. And by continuity of T, which is the sequential continuity we mean, it means that Tx star will also converge to x star. Now, having seen this, uniqueness follows immediately. Since Tx is equal to x and Ty is equal to y, then x must be equal to y. That completes the proof. Now, let's look at an example of a contraction map. We show that f of x, which is equal to 1 over 2 sine x, is a contraction mapping. How do we show that? Now, we say that since f prime of x is equal to 1 over 2 cos x, applying the mean value theorem will give us that the absolute value of f prime will be less than or equal to 1 over 2. Therefore, we obtain that the contraction mapping here, or the contraction constant, is 1 over 2. Okay? Or the Lipschitz constant is 1 over 2. So since we're able to find the contractive constant, then we'll say that the function is a contractive mapping. Let's look at nonlinear spaces. By definition, we say that let X be a vector space over R or C. R is a set of real numbers, then C is a set of complex numbers. A function defined in this way, norm of norm implying that x, such that x goes to 0 to infinity, that is positive r, is a norm if the norm of x is 0 whenever x is 0, and the norm of a scalar multiplication here is equal to the scalar times the norm. And the third condition is a triangle inequality. Once you can prove these 3 points, then you say that the vector is a norm. Now let's look at another example known as the Euclidean norm. Say let x equal to r root, the Euclidean norm. Then you define your norm of x1, x2 to be the square root of x1 squared plus x2 squared. Now carefully, you're going to see that all the properties of norm can be proved, can easily be seen. Number one is that this norm is always positive, and it can only be 0 where x1 and x2 is 0. Number two is scalar multiplication. The scalar will still come out. And number three is triangle inequality, where we are going to see in the near future how it is done. So we believe that the triangle inequality holds here. Okay, either using the Minkowski or the Holder's inequality. Now, LP norms. We also have LP norms defined this way: summation of the absolute value of xi raised to the power p, or raised to the power 1 over p. We can also show that LP norms are norms. They're always 0, or positive, sorry, and can only be 0 if x is 0. Their scalar product can actually be seen, and Minkowski inequality can be used to show their triangle inequality, thereby proving that it is a norm. Now, hopefully, I want to believe that you know what LP norms are. These are sequence norms. Okay. Now, incomplete nonlinear spaces. In this particular course or topic, we're actually interested in the incomplete norms. Okay. And of course, we know what is a complete norm, where the Cauchy sequence converges to an element of the space. Then incomplete will be the reverse. And let's take some example. Example 1, we want to show that the continuous function over a closed and bounded interval AB is not complete. Now we can use this formula here, defined by f of nt ranging from 0 to 1. Okay, and the middle here will be n in bracket t minus a plus 2 over b. Don't forget, always remember that your a is this a here, and your b is from the closed and bounded interval b. So very soon we are going to see specific examples where a and b will be replaced by real numbers. In that case, you should be able to simplify properly. So this is for illustration purposes. You see, at the end, we're able to show that the continuous function over a closed and bounded interval AB with the integral norm defined on it is not complete. Now, let's look at example 2, where your A is -1 and your B is 1. You can see by the time you substitute into the A and B we have in example 1, this is what you're going to have. And the graph will look like this. When you plot the graph of this sequence of functions, you have this. Now, when you continue, you see that from the graph, we're able to see that this norm converges to 0. Hence, Cauchy. Because it converges to 0, it's Cauchy. Now, you now move ahead to show that it is not complete. Now, we have been able to see that that sequence of a function converge to 2 points, 0 and 1. So since it converges to 0 and 1, we say that the limit point is not unique, therefore it's not continuous at 0. Okay, thank you for listening.